Welcome to the course of Digital System Design. In this lecture, we will look at the finite state machine models. We will look at the two types of finite state machines, namely the Melay FSM and the Moore finite state machine. We will define them, we will understand how they are different from each other, and look at a couple of examples for the design of Melay as well as Moore finite state machine models. Good. So far we looked at the combinational circuits as well as the sequential circuits. In the case of the sequential circuits, we look the sequential circuits as a counter which goes through certain binary numbers in a particular manner, and looked at how these counters can be designed using different kinds of flip-flops, namely the D, T and JK flip-flop. We looked at the analysis of sequential circuit as well as the synthesis of sequential circuits. Now it's time that we abstract the design of digital systems in a manner that the design process is made more formal as well as having steps which can be carried out in a systematic manner. So we will come up with a formalism, and henceforth we will always look at the digital system design using this formalism. What we will do is we will consider every sequential circuit to be a finite state machine. So it is a machine in the sense that it works on binary numbers or bits and takes some bits, processes it, and then gives out some bit. So in similar to mechanical machines, these are all binary machines, and they respond to the inputs based on their state, and therefore they have some state information which makes the machine to remember the past input sequence and behave according to that. So we will call them as state machines, and these machines will have a finite number of states. Of course, we can even think of machines with infinite number, but such a machines cannot be realized. Okay, with infinite state machines, it should store infinite number of bits and so on. So essentially they have only finite number of states. So we will view the sequential circuits to be more formally as a finite state machine. We will use the abbreviation FSM to stand for the finite state machines. We will use certain techniques in representing the finite state machines. We have already looked at these formal ways of representing these FSMs. They are nothing but the state tables and the state graphs. They allow us not only to represent the machines, define the machines, they also allow us to analyze it or on synthesis also. So we will heavily use this state table and state graph based formalism in order to design complex digital circuits. First thing that we should understand is that we need a way of categorizing the finite state machines. Based on the way the machines or FSMs are being designed, we have essentially two classes of FSMs. One is called as the Melay category of finite state machines, another the Moore type of finite state machines. So the basic difference between the Melay and Moore, which we also encountered to some extent in the previous lecture, is as follows. While the Melay FSMs produces an output which is a function of its present state as well as the present input, the Moore machine's output is purely a function of the present state. We will expand on this concept in the following slides. So a broad uh, block diagram level representation of a finite state machine model is given here. So the machine has got certain inputs. It may be one or more inputs. They are which are external, in the sense that we don't have a control over how these inputs will take different values. They are produced externally and they come and affect this machine. And these are sequential machines, in the sense that they remember the past input sequence, and based on that input sequence it behaves or responds. So it remembers the history of the sequence that is given to us, which means that I have memory element in that one. That is why they are called as the sequential machines. So once we say it has memory, it should be able to store the state in which it is present in the form of bits. So each bit represents a state variable. So there will be a collection of state variables that constitute a state. By state we mean the minimum amount of information that is required in order to characterize the behavior of the machine. Okay, so we might have looked at the state of a thermodynamical systems or a mechanical systems or even electrical circuits and so on, control systems and so on. In the same manner, here we mean by state the minimum amount of information that we need to characterize the behavior of the state. So only if we have additional information, they are redundant. So we will only keep the minimum information, and that is what we call as the state. Naturally, if there are a number of states, we need a way to distinguish one state from another, because in each state the machine behaves differently. So we need to encode this state. So by we mean a way of understanding that the machine is in a given state at a particular time, so that it responds or behaves based on its state. So internally it stores the state information, and because by that we mean the state variables need to be stored. State variables are nothing but bits, because this is a binary machines. It only can store bits and manipulate bits. Okay, so to store a bit we know that we need a flip-flop. So the state information is stored in what is called as a state register, which is nothing but the group of flip-flops, each one storing a state variable which constitutes the state of the machine. So we have a storage element which has a number of flip-flops. These flip-flops together constitute the state register. As we know, a register is the one which has got a number of flip-flops. So in this case, the number of state variables define the number of flip-flops required, and the number of state variables will also dictate the number of possible states to which the machine can reside and behave. If there are n state variables, there are 2 power n possible states. So that information is what is stored in the state register. Note that the state register need not be one big register wherein all flip-flops are put together. They may even be scattered in the whole circuit, but together they remember the different state variables, and therefore they constitute the state register. Okay, they may not be lumped together in one place, they may be even be scattered. But conceptually, it is simpler to put all these the flip-flops together and view it as one state register, and that is what we have done here. And then apart from this state register which stores the state, the dependency between the input and output and the present state, next state, is being characterized by a circuit which is combinational in nature. You may ask, why is it combination, why not sequential? If it is sequential, it has some flip-flops which can always be taken inside into the state register. So we can segregate the two parts of the digital circuit, one that is purely combinational and the other which is purely sequential, in the sense the bare minimum sequential, which is nothing but the group of flip-flops. Any other gates or whatever it is associated with the sequential part is being taken into the combinational part. So it has certain inputs and it also produces some output. If it doesn't produce an output, then such a machine may not be of use, because it only keeps all the information inside it. It doesn't affect the external environment. We cannot make any useful job done out of those machines. And if it does not take any input explicitly, then it has some use, of course, in the sense that it always behave in a particular sequence of in a particular manner. For example, counters are one which doesn't take any input, but the behavior can be easily characterized, and we take the counts as the output. So counters are also in one sense a special kind of finite state machines. So at any given time we distinguish two kinds of states. One is the current state, which the FSM is storing at that time, and the next state to which the finite state machine will go once a clock pulse comes. So because these are synchronous machines, their operations are always synchronized by a clock. So we have shown the clock here, and the same clock goes to all the flip-flops, hence they are synchronous. We will always talk about synchronous sequential circuits when we talk about the FSMs. We don't talk about the asynchronous machines. So the next state which will get stored when a clock pulse transition comes is called as the next state. So we have got the current state, or simply the state of the machine, the input which are external to it, the outputs which go outside and affect the external universe, and then the next state to which the machine will go once a clock transition comes. How the machine works is that, broadly, the state register stores the present state of the system. At every clock period, there will be certain values that will be available in the various bits in the input, and this circuit, merely based on the combinational circuits, takes the input and the current state together and produces output and the next state. So to this combinational circuit we can view the inputs which affects the behavior that the combinational circuit take, or the external input and the current state, and the output to the combinational circuit is the external output and the next state. And when a clock transition comes, the next state gets stored in the state register, which becomes the current state for the next clock period, and based on the input which might have changed from one clock period to the next clock period, a new output will be produced and a new state will be value will be given, which again gets stored, and this goes on forever. So this is how FSM works. Now we will distinguish between these two machines, category of machines, the Melay and Moore finite state machines. Well, to give an example of how the state behaves, okay, you can view the state to be a mood of a person. So if you let us say you have a friend, and then if you cut a joke on your friend, how the friend will respond depends upon the mood. If the friend is in a lighter mood, he will also enjoy the joke. But if the friend is in a depressed mood, he will get more depressed. Or sometimes if the friend is in an irritating mood, he will rather fight with you. So this mood of an individual is very similar to the state of this finite state machine. How the individual will respond, that is either smile back or keep quiet or fight, is very similar to the way this machine outputs. And it's also possible that based on the input you can change the mood of a person. You can encourage a person who is in a depressed mode and bring the person to a better mood. In a similar manner, based on the input, the state of the machine can be changed, and therefore the future behavior of the person, the outputs that are given, can also be changed. So in one sense, sequential circuits have personality. Okay, so we will instead of viewing them as a dumb binary manipulating systems, we will now give a more personify the machines and deal with them. Well, now we mentioned that there are two categories of FSMs, the Melay FSM and the Moore FSM. The basic difference between the Melay and Moore FSM is that in the case of the Melay finite state machine model, the output are a function of the present input as well as the present state. Whereas in the case of the Moore finite state machine model, the output is purely a function of the present state, and it does not depend upon the present input. We will clarify it. So this is the circuit which is also shown earlier, which is more generic, in the sense that if we mentioned that each one, the external outputs as well as the next state, can be viewed as a Boolean function of the inputs which comprise of the external input and the present state variables. If these outputs are actually a function of the inputs, external inputs as well as the current state variables, in which it actively depends upon the input also as well as the present state, then this representation is more apt, because it tells that the external output is dependent upon the external input, present input as well as the present state, while the next state is obviously dependent upon the current state as well as the current input. Okay, because if it does not depend upon the current state, then the new state to which it will go will only be dependent upon the input, then history will not be taken care of. And if the next state is purely dependent upon the present state, then the input will have no say on what states the machine will go. So the next state has to be dependent upon the present state and the present input, then only it can be a machine, finite state machine model that remembers the history and behaves accordingly. Whereas the dependence of the external output on the present input and the state can be observed in two different manners. This is one manner in which the external outputs are dependent upon the present input as well as the present state. The other way is that the output is purely a function of the current state. So then this block diagram representation is more apt. Here we will see that we have a combinational circuit. Of course, the state is stored in these flip-flops, that is the state register driven by a clock, and there are external input as well as the present state. The next state depends upon the both the input as well as the current state, and it gets stored, and the output is dependent upon only the state. That is why we have not mentioned the output as from this diagram. There is another logic which is again a combinational logic which captures the functionality, the dependency of the external output with the present state. Now you may wonder, In the case of Moore machine, will it affect the output at all, or outputs are independent of the input sequence? The fact of the matter is, external output sequence is affected by the input sequence, but not directly but indirectly. The input sequence affects the states visited by the machine, and in turn these states decide the output. So the input will not immediately affect the output in the present clock itself. It will only decide the state to which the machine will go, and in the next clock period its effect will be shown in the form of the output that is produced. So that is the difference between the Melay and the Moore machine. So with this in mind, so here we have shown if there are n bits that are stored, n state variables, then there are n bits being stored in the state register. Let there be M1 external inputs lines, M2 external output lines, and the next state is again obviously n. So this combinational circuit takes M1 plus n inputs and produces M2 plus n functions of these inputs. So the same holds good here, but only thing is that M2 is purely a function of n, whereas this next state n functions are based on M1 plus n input signals. We will now look at an example for the two machines, Melay as well as Moore machines. For that we will take a classic problem that is encountered more often in the design of digital systems, which is called as a sequence detection problem, and the machines are therefore called as the sequence detector. What basically does is, you have a sequence of inputs that are coming. We look for a particular pattern, binary pattern or a sequence present in the input sequence, and detects it and respond telling that whether the pattern is detected or not. Whenever the pattern is detected, we respond differently, indicating that a pattern has been detected. Otherwise, we will tell that pattern is not detected. That is what we mean by a sequence detector. But you can see that many finite state machines, models, which takes in certain input sequence and produces an output sequence, their response can always be viewed as a sequence detection problem, because based on the different state to which the machine can go, for certain input sequence it produces an output sequence. The outputs depend based on the state as well as the input. So you can always view that whenever certain bit pattern comes, then only the machine responds. So it can be viewed in a generic manner that as a sequence detection problem. So you should not view that sequence detection is a very particular category of designing digital system. It can be more general. So the problem that we have in our that we are going to address is as follows. We need a circuit that will examine a string, a 1-bit sequence, to keep it very simple, of zeros and ones, of course, because we are looking at only bit sequences. That is applied to an input called as X input to a machine. It produces an output Z, which takes a value 1 whenever a particular bit pattern or a sequence is present in the input sequence, and 0 otherwise. So this is the broad definition, and let us take a particular bit sequence, and for that we will design the machine. We will take this simple example of a bit sequence which is 101. So the problem boils down to, there is only one input and one output. That keeps the problem very simple. In general, there can be multiple inputs and multiple outputs. Based on different combination of different bit patterns and different input sequence, the machine can behave and produce different kinds of outputs in their different output bits. But here There is only one input and one output. X is the input, Z is the output. And what is the pattern we are looking for? The pattern is 101. And we are defining that whenever we find a clock period in which the sequence one, we always, of course, this is a synchronous machine. Every bit lasts for one clock period. We view the sequence at every clock period. The input bits are defined in every clock period, and there is a particular output bit being given for one clock period and then changes in the next clock period. So we always discretize the time and view it in terms of the clock period, and also represent the input and outputs against those discrete time which is defined by the clock. So what here we are emphasizing is that is whenever we have at any time at any clock period, if we have a sequence which ends at 101, then that has to be detected and the output has to indicate that. How do we indicate it? We have to the output has to basically tell whether a sequence is detected or not detected. So it is just a binary information the output has to provide. So we can use zeros and one for that. We may tell that if a sequence is detected, the output will become 1. If it is not detected, it is 0. So that is how the outputs are defined. Again, what we want is the output should become 1 whenever we encounter the last bit of the bit pattern we are looking for. So at the same time, when we have a bit sequence ending in 101, the output should become 1. In all other cases, the output should be 0. To understand this problem little in a better manner, we will take an example input sequence and write out the output sequence. So usually when we deal with design of a Melay or Moore machine and view it as a sequence detection problem, the first step that you are urged to do is to take an example and then write out the output sequence for a given input sequence. Because it may appear that the problem is clear from the statement, but problems are often stated in English language and it may be ambiguous. So we need a clear understanding of what how the machine responds. That clarity will come once we have an example and explicitly write out the output for that. That is number 1. Number 2, of course we can give any arbitrary input sequence and figure out based on the rules specified an output sequence, but they may not capture the essential features of the machine. So you have to judiciously choose input sequence that has all the peculiar ways in which this input pattern can appear, and accordingly find out the output sequence. Then only the problem will become clear. Now the question comes, how do I pick up the input part sequence? It's just an example. Yes. To begin with, you may not know what would be a right way of picking up an example input sequence and writing the output sequence. But as we look at more and more examples, you will become used to picking up the right input sequence as a test case for which the output sequence you can arrive at. Okay, it's little rather it comes up with experience, and it will soon become obvious once we look at few examples. So here is an input sequence X and corresponding Z that we have arrived at against the time which is given in terms of the clock period, 0th clock period, first clock period, second clock period, and so on. So what we are looking for is a bit pattern 101. So we are looking for a pattern 101, and whenever we identify a clock in which we have the last bit of this bit pattern, then only we have to respond. For that, what we can do is we can take a window of 3 bits and slide it over the input sequence and compare that content. It's a 3-bit window. Compare the content. We will slide it 1 clock period at a time, and every time we after sliding, we compare the content of the window and check whether a 101 is present. If so, we should immediately respond. So imagine, to begin with, that there is a window of this size. Initially it will be 101, 001. As it slides, you will have 011 and then 110, and it goes like that. Then we will have 101. Now if we keep comparing, now 101 is what we are looking for, and this window exactly as 101, and we are at the ending bit of the bit pattern. So we should respond. So until this time, we should be outputting a zeros in the Z, and at the same time, when the last bit of the input pattern has occurred, we were to produce a 1. Now we are designing a Melay machine. That is why it responds immediately to the present input. So it responds with an output which is dependent upon its state as well as the present input. That is why as soon as the last bit of the input sequence occurs, immediately it responds. At the same time it responds. So in that sense, it is a Melay machine. Again, now we will continue with this window, sliding of this window. If you look at 0, 1, 1, the pattern is broken. Again 1, 1 means the pattern is broken. When we come to 1, 0, 0, okay, when we slide it here, once we get a 1, then this 1 can be a first bit of a pattern. Okay, so if we look at a 1, this can be a first bit of a pattern. And then if we get a 0, it can be a second bit of a pattern. So we should remember that every time we get a bit, we should check whether is it have we got at least the bit sequence partially, and further on are we getting the right bits which matches with the bit sequence you are looking for. So whenever you get a 1, the machine has to remember, okay, this 1 means it can be the first bit of the pattern we are looking for. If a 0 is followed by a 1, it has to further remember that a second bit of a possible pattern. Why possible? Because only still the last bit has not come. We don't know whether the pattern is complete or not. So it can be it is the second bit of a possible bit pattern that has come. So that is what we remember, the machine has to remember. That is what we call the state. Next, if you look at this one, now here let us look at, we have a 1 first bit, possible first bit, followed by a 0, possible second bit, and then a 1, which means yes, we have an input sequence 101, and at the same time when the last 1 has occurred, we output a 1. Until that time, in these all are zeros. Now again there is a 0 and followed by a 1. Now if you look at it, at this 1 also we have a pattern 101 if you look backwards. If you look at this 1, if you look backwards 3 bits including this bit, the pattern 101 exists. So again, according to the specification, we should output a 1. So this is a special case in which this bit is the ending bit of one pattern and it is the starting bit of a new pattern. So in this case, you should remember the information that when you get this last one, you should remember 2 things. One, the last bit of a pattern has occurred, you should output 1 accordingly, and this bit 1 can also be the first bit for a new pattern. Whether it is a pattern or not will only be evident after you receive 2 more bits, but you should also remember that. So this is what this example reveals. You may also have a case where we will tell that whenever you get a pattern of 101, the machine responds, and then it resets and looks for a non-overlapping pattern again in the input sequence, which means that we should not having an overlapping 102 101s. We need a case, a machine, wherein after getting a pattern, the machine resets, forgets everything and looks for a new set of bit patterns. If that is the specification, then your design has to be totally different, and this example is the output will also be different. So that all depends upon the specification of the problem. This is a problem where overlapping bit pattern is allowed. That is implicitly given here. Whenever a prescribed input sequence occurs, that's what it tells. But when we say that the machine resets and looks for new pattern or a non-overlapping pattern, then the output sequence will differ and so on. So all these, if you are not clear, you should again go back and then ask the person who have specified the problem, what do you really want? Is overlapping sequence allowed or not? And get it clarified. All these doubts you will come across only when you look at an input output sequence and get it clarified, and then your design can proceed. That is why I have emphasized enough that you always try to come up with the input output sequence and understand the problem before proceeding to design. Now, how do we design? The first step usually that is carried out is to come up with the state graph. First, it is a very pictorial ways of solving the problem, and human beings are very good at visualizing things and visualizing solutions. So to come with a state graph is more easier for our brain rather than to come up with a state table or with a circuit and so on. We will see how the state graph emerges when we go through this problem. So let us say the machine is in a given state where it has not detected the bit pattern at all. It has not even detected the first bit of a bit pattern. Okay. So that state we have to give a name for that state. We could have given a state start state or A state, B state and so on. And because we can conventionally use the symbol S to stand for a state and a subscript to distinguish one state from another. So we use the symbol S0 to define the state. As we get more and more state, we will call it as S1, S2, S3, S4 and so on. You could have as well used A, B, C and so on. Well, so S0 is a state by definition is a one where we have not even encountered the first bit of a pattern, which is a very right starting point. Then what we do, in this state the machine looks at the bits sequence that is coming and looks for the pattern. At every time it is going to get only one bit. So it can only look for whether that bit, is it the first bit of the pattern it is looking for or not. That is what it can do. It can only scan one bit at a time. So what is the first bit of a pattern? 1. So it waits for 1. Suppose you get a 0, then what you should do? You still haven't got the pattern, so you should still wait. What do we do? Should we go to a different state? Need not be. It can be the same state, because S0 by definition is a state where not even the first bit has occurred. So if you get a sequence of zeros which doesn't even signify the first bit of the pattern, you can continue to remain in the same state S0, because you don't need to remember the sequence of zeros that you have got, because that has not told anything. You can forget about it. Only remember that not even the first bit of the pattern has occurred. Okay, so that is where we tell how much of history we have to remember, we have to observe. It is only that much or the minimal amount that is required to characterize the behavior of the machine. The behavior of the machine in this case is to respond with a 1 for a 1 over. For that, this is enough. Okay. So whenever there is a sequence of, whenever a 0 comes, it remains in the same state yes now. And what does it output? So we have we are using a Melay approach to solve this problem. Later on we will use a Moore approach to solve this problem. So if you ask a question, what approach should I use to solve this problem? It is up to you. You can either use a Melay approach or a Moore approach. Both, you can always come up with a design based on either Melay or Moore to solve any given problem. First, we are looking at a Melay based approach. So for every input, there has to be an output in the same clock period. So accordingly, this is the formal method we are using to represent the input-output behavior, which we have already seen these examples in the previous lecture. Again, to give this one, S0 with tells that it is a state, it is a node in a graph, and we have a directed arcs. The direction indicates to which state we go, that is what the directions. We have labels on those arcs. So this tells that from S0 we go back to S0. The labels will, the way we denote the label is what is the input and correspondingly what is the output. We separate the input and output by a dash. Here 0 dash D0 means 0 is the input and 0 is the output. Later we will have like 1 bar 0 means here 1 is the input and 0 is the output. Here we will have 1 is the input and 1 is the output. So this is how we label the one. If you have 2 inputs and 3 outputs, you may have a label like 10 bar 110, which means that the 2 inputs are 1 and 0 and the outputs are whatever that is specified after the dash. So here whenever we get a 0, we output a 0 and remain in S0. Now if a 1 occurs, because in S0 the next bit can be either 0 or 1, we have to handle both the cases. We have handled the 0 case. When a 1 comes, what do? The machine should recognize that it can be the first bit of a possible bit sequence, and when we say it remembers, what does it mean? It has to go to a different state. That state characterizes the fact that it remembers that the first bit of the pattern is occurred. So we will use one more state called as the S1. The difference between S0 and S1 is that S0 indicate that not even the first bit of the sequence has occurred, whereas S1 inherently means that the first bit of a possible sequence has occurred. That is the only distinction between the state S0 and S1. So again, when 1 occurs, it goes to S1, but still it outputs 0 because it is not a completion of a sequence. Now in S1, that is a 1 has occurred, you have come to S1. If again a 1 comes, what it means? The sequence has broken. We were expecting 101, a 1 has occurred, we have come to S1. Again a 1 has occurred while we are expecting 0. So the pattern is broken. But what do? Should we go back to S0 and start looking for the new pattern? No, because a 1 has occurred, that 1, that is we have got 1 followed by a 1, that second 1 can be the first bit of a new pattern, which is what S1 characterizes. So it is better you go back and stay in S1 and not go back to S0. So when 1 occurs, you output a 0 and remain in S1. So S1 always means that the previous bit that we have got is a 1, and before that, that is the first bit of a sequence. Next, after that, suppose in S1 a 0 comes. What it means? From S0 we got a 1 and then we got a 0. which means that it can be the first 2 bit of a sequence. That needs to be remembered. How do we remember it? By going to a new state. You cannot tell that I will remain in S1 remember. See, this is not the states by themselves. It's not that S1 can remember 2 different things. Each state means it stores something, and that storage corresponds to a particular concept being remembered by the machine, and therefore we have to generate a new state if we have to behave differently. The behavior in S1 and S2 are different because here only first 1 bit has occurred, here 2 bits have occurred. So we have to go to a new state, call it as S2, and still we output a 0. Now we have got a 1, 0, and then if we get again a 0, what do we do? Unfortunately, the last bit of a possible pattern is 0, and therefore it is not a pattern. What do? We cannot output a 1, pattern is not detected. And where do we go? Should we go to S0 or S1 or remain in S2? We have to go to S0 because what we have got is a 0 that is not even. 1, 0, 0 means it is not even the first bit or even the second bit of a pattern. It is not a first bit because it is not 1, and it is not a second bit. If it were a second bit, it would have been a 1 followed by a 0. It is now 1, 0, 0, a 0 followed by a 0. So we have to go to S0. So we output a 0 and go back to S0. But now, if you are very lucky, we get a 1 in S2. What does it mean? We have got a 1, went from S0 to S1, and then we got a 0, went from S1 to S2, a 1, 0, again a 1. We have hit upon this sequence. We should output a 1. That much is clear. Where do we go? We go to a state which tells that a pattern has been detected. Okay, that is very clear. That is how you produce a 1. Well, should we generate a state called S3 where we go when we get a 1, producing a 1 from S2? Well, if we do so, then it simply remembers that a pattern has been detected. But we should also remember one more thing, as we saw in this case, that is that last one that we have got can be the first one of a new pattern. And which remembers that? It is S1 that remembers that. So if we go to S1 by producing a 1, we are not only satisfying the criteria that we are detecting and outputting a 1, we are also going to a state where the first one of a new pattern, possible pattern, is also found out. So we should go to S1. So this is what we do. Now we need to, once we run through these cases and generate states and arrive at these graphs, then next thing we should do is all possible conditions of inputs occurring in different states taken care of. That is, in each state we have to check whether the occurrence of both zeros and ones have been taken care of. That is, in S0 you can get a 0 or 1. So there are 2 transitions, one with 0, one with 1, taken care of. Here again in S1, transition with a 1 and transition with 0 taken care of. In S2, transition with a 0 and transition with 1 is taken care of. That's it, and it is a closed one. We are not going to a new state. In every state, every possible occurrence of the values of the input bit has to be taken care of. Then only the machine is complete. So here we get a graph which is closed. Okay, all states have been viewed and all possible inputs that can occur in each state has been taken care of. Then the machine is complete. As a cross check, you can also tell, see, here is a case where we have a 101 followed by a 101. Still this can go on. A 101, 10, 10, 10, 10, 10 and all if it comes. So there is a sequence of overlapping 101s, after at the every one there has to be a 1. Will that occur here? Yes. Look, a 1, 0, 1, you go to S1. Again there is a 0, again there is a 1, again there is a 0, n. You will keep on revolving in this cycle, every time outputting a 1 whenever we get a 1. So the machine is now complete. Well, to arrive at this kind of a machine, we have to apply the logic and our clear understanding of the problem and do it. Well, this takes some kind of an experience to arrive at the machine. Beyond that, we cannot codify the principles in arriving at the state graph. It comes with experience and you have to develop that expertise. Okay, and you can do so only by solving many problems. The next step is to convert the state graph into a state table, which is one step closer to the actual design. So in the state table, as we saw that there are many ways of laying out the state table, all possible inputs and all possible outputs, then it's mostly the truth table form. Here what we do is, for every present state, what will be the next state and what will be the output for the two possible inputs that can come. That is what is being listed out. So this state table has got two parts. One is the next state part and another is the output part. We will all sometimes call it as the next state table. This together constitute a next state table, and the first column and the third column tells the output table. We have clubbed both together because the present state is common for both. So this is what is illustrated. So this is a different way of writing out the state graph. Suppose the present state can be, there are three states, S0, S1, S2. Present states can be S0, S1, S2. And the input can be X, can be 0 or 1. For each of these cases, we write down the output state, next state. So from S0, when the input is 0, we go back to S0. So from S0, when the input is 0, we remain in S0. When the input is 1, we go to S1, which is given here. And we can also write out the output also. For in S0, when the input is 0, the output is 0. When the input is 1, then also the output is 0, which is again given here. Coming to the state S1, for input of 0, we go to S2. In S1, when the input of 0, we go to S2. When the input of 1, we remain in S1. In both cases, we output only S0. Coming to S2, for an input of 0, we produce S0, we go to S0. For 1, we go to S1, which is given here. How is the output? For a 0, we output a 0. For a 1, we output a 1. For a 1, we output a 1. So this is the state table. Now here we have retained the label of the state and come up with the state table. Again, this is only a different way of presenting the state graph. Now in order to come up with the design, we have to encode the state. The states have to be represented as binary numbers. That is called as the encoding of the state. We should use bits to store a unique pattern for each state. There are 3 states, therefore we need at least 2 bits for it. A single bit can only differentiate 2 states. If you have 2 bits, it can differentiate 4 states, but we need only 3 states. Of course, there is 1 state which is not used. So we have to have 2 state variables. You can call them as A and B. Then we have to associate to each state a bit pattern, a particular combination of A, B. We can treat A to be most significant and B to be least significant. And we may probably tell that AB, if it is 0, 0, it designates S0. If it is 0, 1, it is S1. 1, 0, it is S2. and 1 1 represents the state S3 which is not being used. So here what we have done is we have treated the subscript zeros to be a decimal number, 00, this to be a decimal, and the corresponding bit pattern, this binary number is 00, and we have used that same bit pattern to stand for the value of A and B, which are used to encode the state. If you do so, this is called as a straight binary assignment of the state variables to the state. Once we do this one, we have to rewrite this table. I have not shown it here, we will do it later. I am just giving it that information now. So you have to represent the present state in terms of the state variables AB as 0 0 0 1 1 0, and the next state variables are A plus B plus, which again has to be encoded. Whenever there is an S0, we have to put it as 0 0, for S1 0 1, S2 1 0, and so on. Once we have this encoding, then the state table can be used. We can realize A plus and B plus in terms of A, B, X, and we can also come up with a function for Z and use two flip-flops and the desired gates to realize the next state A plus B plus and Z in terms of A, B and X. This is how it is going to be. We will see the example of design of a circle of a circuit in a later example. Okay. First we will at least look at the state graph and be familiar with it. Now let's say we want to solve the same problem, now using a Moore approach. How do we do it? So now that the problem is clear and the example is also clear, overlapping 101 should also be detected. Okay, how do we do it? So here we will see how the Moore machine will work. The Moore machine, the output is only a function of the state. So which means that when an input changes, it does not immediately affects the output. It triggers a change in the state only, and the changed state it responds. So if a 101 pattern occurs, the Moore machine cannot immediately respond with a bit telling that the pattern has been detected. The machine has to go to a state where it indicates that a pattern has been detected. So it outputs one clock period after the ending of the pattern. Okay. So here if you look for this one, here is where the pattern has occurred. While the Melay machine immediately outputs a 1, Moore machine cannot output a 1 at this point. It affects the state. Of course, we don't represent the state information here. We affects the state and indicates that this pattern has occurred in the next clock period after the occurrence of pattern. So the 1 occurs here in the Moore machine, whereas this 1 occurs along with the last bit of the pattern in the Melay machine. Again, if you look at for this one, in this 2 example, as soon as the first 101 occurs, while the Melay machine outputs a 1, Moore machine outputs a 1 bit later. Similarly, the second 101, overlapping second 101, is also detected 1 bit later than the second 101. So there is a lag of 1 clock period in the production of the output by the Moore machine. That is the only difference between Melay and Moore machine. Both detects the pattern, but the way they output is, there is a lagging of 1 clock period in producing the output by the Moore machine. Okay, that is not to be viewed as a disadvantage of the Moore machine. It is only the way the machines behave. Well, now in the case of the Moore machine, the output is purely a function of the state. That is what we have already mentioned it. The output is purely a function of the state. So the outputs are not dependent upon the present input, which means that the outputs need not be put along with in the label which is mentioned over the transitions, because from a given state, based on the input, there are 2 transitions. one for 0, another for 1. And if the output is dependent upon those input, then you have to put the corresponding output for the two possible transitions that we have. In S0, there can be the input can be a 0 or 1. Based on the output, if it is also dependent upon the input, you may have a 0 here, we may have a 1 here. So you have to put the output in the label along with the as a part of the label in the transition. Whereas for a Moore machine, the output is a function of only the state. So you can as well indicate the output along with the state. That is, in the node itself we can mention the output. So let us assume that we are in a state called S0, in which not even the first bit of a pattern has been detected, and therefore the output has to be 0, and therefore it outputs a 0 while it is in the state S0. Now you look for bit one after another. If the bit that has arrived is 0, we have to remain in the same state, because it is still we are looking for the first bit of a pattern. When you get a 1, well, you should remember it, so you generate a new state, call it as S1, but still output as 0, because it is only the first bit of the pattern. It is not a complete pattern has come. So you go to S1 and output as 0. Now S1 indicates that a first bit of a possible sequence has come. Again, if there is a 1, well, we have broken the sequence, but this 1 can be again the first bit of a pattern, so you remain in S1. On the other hand, if it is a 0, it could be the second bit of a possible sequence, so you go to a new state, call it as S2, but produce still only a 0, but because only 2 bits have come. Now in this case S2, when a 1 occurs, the pattern has come 1 0 1, but now you cannot, the Moore machine cannot output when the last bit has come, because it cannot respond for the 1 which is given, which has come in that clock period. What it has to do is it has to go to a state and then only respond. So it when a 1 comes, it goes to a state S3 and responds to the 1 in that one. By the by, you should remember that the machine remains in a node or a state for 1 clock period. When a clock transition comes, this state transition occurs in no time. It doesn't take any time in moving from one state to another state in an ideal machine. Whereas in each node of the state graph, or in each, it remains for 1 clock period. So it remains here for 1 clock period. When the transition comes, immediately it makes a transition to the next state and then remains in that state for 1 clock period, and so on. So be careful, be attentive and take note that it remains in the nodes for 1 clock period, and transitions does not consume time. It is immediate. Therefore, from S2, at the end of the clock period, when a 1 comes, it remembers that it has to go to S3. At the end of the clock period, it goes to S3, and then in that full clock period, 1 will be there when it is in the state S3. Other things can be easily taken care of. In S2, if a 0 occurs, that is 1 0 0, you have to obviously go to S0, because it is the no pattern is there. And here in S3, if you have a 1, it can be the first bit of a new pattern is broken, so you go to S1. And in S3, if a 0 comes, this can be the second bit of a new pattern, because you have a 1 0 1 pattern is over. Again a 0 means again it can be a second bit. Again you come to S2. Again if there were a 1, you come to S3 outputting a 1, and so on. So a 1 0 1 0 1 0 means you will remain in this cycle. So again you have to check whether all states have been taken care of. By that we mean, have you analyzed all states, and each state whether both possible values of the input has been analyzed and transitions represented and so on. Then convert the state graph into a state table. How do we do it? Again, you have the present state, then list out the next state. For the two possible input values you can get, x equal to 0, x equal to 1. Then the output. The output for the Moore machine is only a function of the state. It is not going to depend upon x. So you don't need two columns, one for x equal to 0, x equal to 1. You just have only one column for the output. That is a function of state. So when you are in S0, see there are 4 states, S0, S1, S2, S3, that is given here. When you are in S0, see the outputs can easily be given. Whatever the value of the output along with the state, you just have to represent. Only for S3 it is 1, for all other states it is 0. And what do we do? When you are in S0, for x equal to 0 you remain in S0, for 1 you go to S1, that is given here. In S1, for 1 you remain in S1, for 0 you go to S2. So it is S2 and then S1. For S2, for 0 you go to S0, for 0 in S2, for 0 you go to S0, for 1 you go to S3. In S3, for 0 you go to S2 and of 1 you go to S1. So this is the state table. Again, the next step is to encode it using bit variables A, B. Incidentally, the Moore machine has got 4 states and luckily only 2 bits, A and B. Bits, number of bits does not increase. And then we can realize it. After encoding with A, B state variables, we can realize it. Well, now we will now look at a more complex example of Melay and Moore machine. I am going to take a very detailed design for a Melay machine. I will go through it in a separate lecture. Whereas this Moore machine example is rather simple. We will complete this lecture by only discussing this example. So here is a case of designing of a Moore based sequential finite state machine for a problem of encoding bits which needs to be transmitted from one computer to another. So we will have 2 computers, one we will call it as a transmitter, another a receiver. We may have a link between them, wired or wireless link, through which we have to send bits. So we will call that as data bits. So some information is encoded in the form of zeros and ones and they have to be sent. Maybe images, videos or raw data and so on, textual information and so on. So the bit sequence can be 0, 1, 1, 1, 0, 0, 1, 0 and so on. How do we encode it and then send it? So one obvious way in which you might try to encode is use two different voltage levels or physical, you encode it as a physical variable and then send it. Voltage levels, or in the case of the intensity of a light, if you are using an optical communication or some other mechanism. So you can use a 0 level, okay, of the physical variable, 0 voltage level, to encode 0 and a 1 for encoding the bit 1. What we do is we are transmitting a 0, 1 and so on. We have a clock, okay, which specifies what bits we are sending. It's always with respect to a clock. And each bit lasts for 1 bit duration, which is equal to 1 clock period, which is known to the sender and receiver, transmitter and receiver. So that can be 5 or 10 nanoseconds. So each clock period lasts for 10 nanoseconds, which is the clock period, which is also the bit period. So for the entire 10 nanosecond, it will be 0. Then for the next 10 nanoseconds or 1 clock period, it will be 1 and so on. Okay. So this way of encoding, where when there is a data bit 0, you send a voltage level of 0 for one full clock period. For a 1 you send a voltage level of 5 or so for one full clock period, and so on. It is called as the NRZ encoding scheme, also called as the non-return to zero encoding scheme. Okay. Why it is called so will become obvious soon, non-return to zero. So this way we are doing it, very obvious and methods of doing. But it has got certain issues when it comes to implementation. Those issues are related with a communication system, which at this point we cannot go fully in depth, but I will simply motivate you or what problems we may encounter. Well, in order to actually send this bit sequence and detect it properly, both the sender and receiver has to synchronize their clock exactly. By that, they should both know when the clock starts, period starts, and when it ends. So, when a sender sends a 0, the receiver will get after some propagation delay, but if it knows when a 0 clock period has started, when it has ended, then it can sample the value of the physical variable at the middle of the clock period and detect whether it is a 0 or 1 by looking at the what it has got. Of course, it will be little corrupted, but we can find out and then reconstruct whether it is a 0 or 1. So, in order to sample it exactly at the middle, okay, approximately at the middle, rather, it should know when the clock period starts, when it ends. So, the frequency should be correct. There should not be drift in frequency, number one, and they should also be synchronized. Their beginning and ending they should know exactly. If the receiver assumes that the beginning is here and ending is here, it may sample it here, which we may get an inappropriate value. Synchronization is important, and for that to happen, okay, we should try to avoid long sequence of ones and zeros in the NRZ encoded stream. If you have a sequence of long sequence of ones, you will have this variable remaining like that for long duration. Then there won't be any transition between this, and it will soon lose synchronization. We cannot go beyond this point to emphasize why synchronization is lost, but the lesson that we should understand is that long sequence of ones and zeros should be avoided. So how do we do it? The data that we obtain can have a long sequence of ones. We don't have a control. Whatever data we get, we have to send it. So the way we can do it is through encoding. Such an encoding scheme which avoids this problem of long sequence of zeros ones is a Manchester encoding. Here what we do is we use a clock, we have called it as clock 2, which has twice the frequency of the base clock with which the zeros and ones are being created. Twice the frequency means it has a period which is 1/2 of it. And let us view both. Imagine the clock of the base clock based on which the zeros and ones are produced. Here, with respect to this clock has twice the frequency and half the period, and both, let us say, they are synchronized. So with regard to this clock, there are 2 clock periods for every 1 clock period of the base clock. So now what we do is, when we have a data bit 0 which is encoded as a full 0 during the entire clock period of a base clock, what we do in the Manchester encoding is that we generate a 0 for 1/2 of the base clock and then a 1 for the next half of the base clock. Or in terms of the new clock 2, for 1 clock period of clock 2 it will be 0, for the next clock period of clock 2 it will be 1. This is how a 0 is encoded. When it comes to 1, a data bit 1 which is encoded as a full 1 for the entire clock period of the base clock, it is encoded as a 1 for the first half clock period of the base clock, followed by a 0 for the next half period of the base clock. Or in terms of the clock 2, which has got two periods, clock periods for every base clock period. It is a 1 in the first clock period of the clock 2 followed by a 0 in the second clock period. So, or now if you view everything with respect to the clock 2's clock period, see clock 2's clock period is only this much of duration. If you have a data bit 0, that will be encoded as 2 zeros in NRZ, but here we will convert the 2 zeros into a 0 followed by a 1. If you have a data bit 1 in the data, in NRZ it will be encoded as 2 ones in the perspective of the clock 2, but for Manchester it will be encoded as a 1 followed by a 0. And this is how we do. If you do this kind of a coding, we can easily see that always there will be a transitions in the middle of this one. And of course here we are going to sample at this point. You will always be able to sample it, construct the Manchester encoded sequence and then construct the data sequence. Okay, so the sum and substance is as follows. Let us view only from the point of view of clock 2. Okay, so you would get data bits, which will be a bit 0, data bit 0 or data bit 1. Data bit 0 will be a 0 followed by a 0, 0 followed by a 0. If it is 1, it will be a 1 followed by a 1. And then we will have a 0 followed by a 0 or 1 followed by a 1 and so on. Okay, so what you have to do? A 0 followed by a 0 has to be converted into a 0 followed by a 1. A 1 followed by a 1 has to be converted into a 1 followed by a 0. This is what we have to do. So here we have a machine which we can arrive at based on this problem. Let us assume we have converted a bit, whatever may be that bit, okay, and we are ready to convert a new bit. How do we respond? How do we behave? At the end of one conversion, you may be in a state. State represents in which bit you have outputted recently. You might have outputted a 0 here, or you might have outputted a 1 like this. So at the end of a bit conversion, see what are bit conversion periods? These are all, these dashed lines are the bit conversion period. At the end of one bit conversion, and if you are ready to convert the next bit, you may be in the state where you have produced a 0 or a 1. For example, here is this is a bit conversion period is over. Here is a case where you have converted a bit and you are in a state 0. And this is a case where you have converted a bit and you are in a state 1. So there are two possible initial states you can be. One, we will call it as S0 and put a 0. It's a Moore design, so you output a 0, telling that you are converted a bit, you are ready to convert a new bit, but you are in a state we have produced a 0. Or if you are in this state where you have finished a bit conversion, ready to do a next bit conversion, but you have outputted a 1. These are the two initial states. Now, if a new bit that comes, if it is a data bit 0, then in terms of this clock 2, there will be a 0 followed by a 0. Then what is that we have to do? We should produce a 0 followed by a 1. So when we have a 0 followed by a 0, we should go to a state S1, outputting a 0, okay, and then go to a state S2 where you output a 1. Why do you need a new state? Because this is in the middle of a data bit. You should respond at this point. A 1 0 has come. The next bit has to be only 0. It cannot be 1. And accordingly, having put a 0 here, we have to produce a 1. All these have to be remembered. That is what S1 designates. So for a 0 followed by a 0, you have outputted a 0. You have gone to a state where you have put 0, followed by a state where you have put a 1. Now in this one state, when you have just when you are in a we have completed converting a bit, and if you are in 0 and then the next is 1, we will look at that one. Okay, if you get a 1, I am looking for an example that is present here, that is a 1 followed by a, oh yeah, it will be a you have, okay, you are in a state where it's 0, yeah, you are in a state where you are 0, you have completed a bit conversion. Now if there is a 1 followed by a 1, you have to produce a 1 followed by a 0. So you have completed, there is a data bit 1, therefore we have an NRZ from clock 2 perspective, you have a 1 followed by a 1. So you go to a state called S3 producing a 1, followed by that you go to a state producing a 0. That is where a 1 1 comes. So that is where a 1 1 comes. You are in a state 0, a 1 1 comes, you go to a state where you produce a 1 and then come back to a state where you produce a 0. That is what this is taken care of. On the other hand, when you are in a state like S2, where a bit conversion is over and you have produced a 1, okay, like this one, when a 1 comes, what do you do? When a data bit 1 comes, it will be a 1 followed by a 1. You have to produce a 1 followed by a 0. So here you are in a state where in a 1 a conversion is over, a 1 followed by a 1, a 1 followed by a 1 occurs. You have to go to a state where you produce a 1 followed by going to a state where you produce a 0. So this is how you respond. So again, after doing this one, you check whether all states are taken care of, all possible input sequences are taken care of. Then translate this into a state table. Present states can be S0, S1, S2, S3. The outputs are purely a function of states. So you write out whatever state outputs are there along with the states, 0, 0, 1, 1, 0, 0, 1, 1. And from S0, what do you do? For a 0, you go to S1. From S0, for a 0, you go to S1. For 1, you go to S3. From 1, you go to S3. In S1, for a 0, you go to S2. For a 0, you go to S2. Incidentally, S1 is a state which is in the middle of a bit conversion, data bit conversion. So if there is a 0, it has to be followed by a 0. 1 cannot occur. So 1 cannot occur, therefore this is a don't care case. In S2, when a 0 occurs, you go to S1. And 1 occurs, you go to S3. In S3, again you are in the middle of a bit conversion. 1 has occurred, it has to be followed by a 1. When that 1 occurs, you go to S0. A 0 cannot occur, therefore it is a don't care. So this is how again after that you will encode this into 2 bits AB and then represent all the states as in terms of bits and then use K-map to reduce it and then populate with gates and then come up with the design. So this completes our discussion on how two examples of how a Melay and Moore based FSMs can be once the problem is stated, how we can come up with the state graph and state table and so on. So we will stop at this point.